So today we're going to go over a kind of an introduction to what astronomy is and why it's important to study it, and a preview of some of the things that we'll be talking about this semester. So astronomy really is an interdisciplinary field. My degree is actually in physics, but I do research in astronomy. But all of these different fields, engineering, you want to build rockets to go into space, computer science, all of our data that we collect now is with computers and cameras, so you need to be able to handle large amounts of data. Chemistry, how atmospheres work, and the chemistry for life, so if we're looking for biology out in space. Geology, how planets form and what their compositions are now. You can think of, like, if you wanted to write a sci-fi novel, if you didn't know astronomy, you would write probably a pretty bad novel. And then art, a lot of the images that we take now that's not necessarily what your eye would see, but they're artistically enhanced so we can have pretty pictures to show people. So pretty much any major you might have, we can think of some tie-in to astronomy. So how does astronomy shape our everyday life? So what is a year and why is it 365 days long? Yeah, so it takes the Earth about 365 days to go around the sun in its orbit. And we can tell that the Earth has completed one of these orbits by looking at the position of stars in the sky. So when the same stars appear at the same part in the sky, then we've done one complete orbit around the sun. What about a month? What is a month and why is it about 30 days long? Yeah, so it's related to the moon cycle and how it orbits around the Earth. So it takes the moon about 27 days to orbit the Earth, and we can tell that the moon has done one orbit around the Earth by looking at the phases of the moon. And we'll come back to this in our next few lectures. What about this? Why are there 7 days in a week? So we have Sunday through Saturday. Why? So when ancient astronomers looked up at the sky, they saw stars, so those behave in normal, predictable ways. But there were 7 bright objects that didn't move like the rest of the stars in the sky. So they assigned very special value to what they called these wanderers, and they deified them. We'll come back to this in one of our future lectures, but for example, Mars is the Roman god of war. So it's not just a planet, but it was a deity to these ancient peoples. And so if you have these deities, you might assign a day to that deity in reverence. So Mars becomes one of our days of the week. And so there's 7 of these, so there's 7 days of the week. And so these are the wanderers that we can see. So there's 5 planets, and then the moon and the sun, which also don't behave like the rest of the bright objects in the sky. And then what about a day? So we have this thing called a day, and it's 24 hours long. So the Earth is spinning on its axis, and it takes 24 hours to do that rotation. But where did that number 24 come from? It's kind of a weird number to divide things into. So ancient Egyptians actually used the base 12 system. So modern society, we use base 10. We have 10 fingers. You count things to 10. They used their knuckles instead to count to 12. So each finger, not including your thumb, has 3 segments. And so on each hand, you can count to 12 using each of those segments. they measured their daytime using sundials. So you have just basically anything that sticks up out of the ground, and when the sun hits it, it casts a shadow, and you can track the motion of that shadow throughout the day. And if you divide your sundial into 12 segments, because that's how they decided how to count, you get 12 hours in your day. Of course, there's a nighttime too, so if you take your 12 segments during the day, you add another 12 segments for night, you get your 24 hours in the day. So the fact that you made it to this class in August, on Wednesday at 10 a.m., in 2025, all of those things are related to astronomy. So you might not actively be thinking about, okay, I'm here in August because the moon has gone around the Earth 8 times this year. But that is how we base our entire system of measuring time, basically. So all of these units of time are based on observations of the sky. Astronomy is different than other kinds of science in that we can't design our own experiments. So in chemistry, if I want to know how chemical A and B react, I just mix them together in some kind of a test tube and see what happens. For astronomy, I can't say what happens if I make a sun that has extra hydrogen or less helium. What happens? So we're constrained with what already exists in the universe. So astronomers have to be very good at observations, and we have to take very careful measurements of what we see in the sky. Okay, so now let's get into how we talk about where the Earth is in the universe and how big the universe is. So where we are in the universe. So this is known as our cosmic address. We are currently on the Earth. The Earth is in the solar system, so that's all the stuff that orbits the sun. Our sun is in a galaxy called the Milky Way galaxy. Our galaxy is in a group of galaxies called the local group, and these galaxies all interact with each other gravitationally. Our local group is part of several other groups of galaxies that are all together in the local supercluster. And then this background image is a simulation of what we'll talk about later, is basically a framework of dark matter that all of the visible matter in the universe is built off of. So the sun is the star that's at the center of our solar system, but we'll study many other types of stars as we go through the semester. So a sun is a ball of gas and plasma that does nuclear fusion and emits light and energy. That is how humans are alive. Planets are the things that are orbiting stars, so they can be rocky like Mars, or they can be gaseous like Uranus. And they don't produce their own light. In our solar system, we can only see them because the light from the sun is bouncing off of their surface and then coming towards the Earth. Moons are the things that orbit planets. So the planets are orbiting a star, and then the moons are orbiting those planets. And so these, in the solar system, these are going to be rocky or icy. And another word that we might use is satellite, just meaning something that orbits something else. Asteroids are things that orbit the sun, but they were not big enough to become planets. Most of them live or reside in between the orbits of Mars and Jupiter in our solar system. But these are smaller rocky objects. Comets are further out from the sun than asteroids, and these are made out of ices. So again, these are still objects that are orbiting the sun, but they are not big enough to be called planets. The solar system is all of the things that orbit a given star. So this is not our solar system, this is a different solar system. That's actually a binary system. So there's two stars in the solar system. One very bright, large star, and one smaller, very faint reddish star. Nebula are large regions of gas that are not in any given solar system. So these are, we'll learn later, these are kind of the nurseries where stars and solar systems are born. So all of these bright things are stars in this nebula, and so nebula can be very, very large. And then galaxies are all of the stars that are orbiting some central point, taking the collection of all those stars together. So there's lots of stars and planets and gas and nebula all in this galaxy. And we'll learn later on what they're orbiting and why they orbit in the way that they do. And then the universe is basically everything that exists. So all the matter and energy, and it's made up of countless numbers of galaxies, which themselves have billions of stars in them. And again, this is a simulation of the kind of lattice framework that dark matter creates, and where the bright spots are where galaxies formed on that lattice of dark matter. Something interesting that happens because of a consequence of special relativity, and that's that light has a finite speed. So that's 3 times 10 to the 8 meters per second, or 300,000 kilometers per second. That's how fast light travels. So in order for light to get from an object to you, it has to travel some amount of distance, and we'll see in a couple weeks how we can calculate that time using distance and speed. But for some common things, the moon is about 1 light second away from us, so the moon doesn't create its own light, but light from the sun reflects off the moon and then comes towards the earth. And so we're really seeing the moon as it was 1 second ago. We're not seeing the current state of the moon. The sun is farther away from us than the moon, so it takes about 8 minutes for light from the sun to get to the earth. So let's say the sun blew up one day. We wouldn't know about it until 8 minutes after the explosion actually happened. Sirius is a nearby star. It takes 8 years for light from Sirius to reach the Earth. And then the closest galaxy to the Earth in the Milky Way is the Andromeda galaxy. And it takes light from that galaxy 2.5 million years to get to the Earth. So because the speed of light is finite, it takes time for it to travel the very large distances that we deal with in astronomy. Because of this, when we look further out into the universe, we're actually looking farther back in time. So you're kind of doing archaeology if you want to think about it that way. If you can see very far away, then you can see the universe as it was very far back in time. So that brings us to the definition of a light year. So that's the distance that light can travel in 1 year. So we said it took 8 years for light from the star Sirius to reach the Earth. So the star Sirius is 8 light years from Earth. light years is a distance, though. It's not a time. So this, if you play Pokemon, this trainer says you're light years from facing Brock, even though Brock is like right here. So you're like 5 steps away. So the game developers made that mistake, and then in a reboot, they tried to cover their mistake and make it seem like he knew what he was talking about. Like, oh, I just meant you're really far away from him, but again, he's just right off the screen. And so, because we're looking, as we look farther back and farther away from us, we're looking farther back in time. So we're seeing the universe as it was when it was much younger. So this is a really powerful tool that we can use to study how the universe has evolved over time. So for example, if you take these different these different distances, then you could study, say, what stars looked like 14 billion years ago, what they looked like 12 billion years ago, and what they looked like 7 billion years ago. And maybe stars that formed at these different times behave differently. We'll learn about different generations of stars later in the class. So here's another conceptual question. So why can't we see galaxies that are 15 billion light years away? Yeah, so because there hasn't been, if the universe is 14 billion years old, then that's the farthest distance that we can see, because that's the most amount of time that light has had to propagate. So we'll learn that the universe is actually expanding, so it is possible that there are things that are 15 billion light years away from us, and they might be very faint. We'll learn about the James Webb Space Telescope a bit later in the semester, and we're actually seeing some very old, very far away things with that telescope. So we are able to see very far things away from us. We just, the light from those very far away things hasn't had time to reach us yet. About this yet, this is just a conceptual question. So if we reduce the sun by a factor of 10 billion, it would be about the size of a grapefruit. So if you shrunk the Earth by the same factor, how big would it be? So you can use the size of the grapefruit to kind of inform what size you think the Earth would be. Yeah. So it's not so small that it would be the size of an atom, but it's not really comparable at all in size to the size of a grapefruit. So it's about the size of the little ball that's in the tip of a ballpoint pen. So very, very small. The Earth is very, very small compared to the size of the sun. But then how big is our entire galaxy compared to the size of the sun? So if we change our scale by another factor of 1 billion, then if we can shrink the size of the galaxy into something that would fit inside of a football stadium, then each star in this scale would be microscopic. So planets are very small usually very small compared to their stars, and stars themselves are very small compared to the galaxies that they reside in. And then what about the Milky Way galaxy with respect to other galaxies? So the Milky Way is one of about 100 billion galaxies. And so if you try to calculate how many stars there would be in all of those galaxies, there's about 10 to the 11 stars per galaxy. And if there's 10 to the 11 galaxies, then there would be 10 to the 22nd power number of stars. And so if you went and counted all of the grains of sand on all of the beaches on the Earth, that would be how many stars there would be in the universe. So these are very big numbers that can be hard to wrap your head around. And we'll be learning about some of these things during the semester. Okay, so the Earth is in the solar system. The solar system is in the Milky Way galaxy. The Milky Way galaxy is in the local group of galaxies, and that group of galaxies is in the local supercluster. And the size as you go into each of these next higher level is orders of magnitude bigger than the previous. So the Earth is much smaller than the Sun. The Sun is tiny compared to the galaxy that it resides in. And all of the galaxies in the universe there's a lot of them, and the distances between them are very big. Okay, so we'll talk about kind of a brief history of the universe, and we'll come back in more detail about this topic later in the semester. So we think that the universe started with a Big Bang where all of the matter and energy in the universe were in a very small, compact region and expanded outward from that place. So over time, you have all of basically everything that could exist in a point of space, and everything expands out from there. So eventually, from that point of space, you can get things like stars forming. Those stars gravitationally attract each other and form galaxies. And in those galaxies, orbiting those stars, you get planets forming. And we happen to live on one of those planets. The gas in these galaxies is not like a permanent thing. So when stars form, they collect a bunch of gas into themselves that they use to do fusion reactions. Those fusion reactions are not infinite though, so eventually stars will no longer be able to do fusion reactions, and depending on the mass of the star, it might blow up, it might collapse into a black hole, and when it does those things, the gas is recycled back into the galaxy, and the next generation of stars are basically formed from the remnants of the previous generation of stars. So within galaxies, the gas is just constantly being recycled. Okay, so the gas clouds or nebula in the galaxies are the breeding grounds for the stars. The stars form and absorb or take in a lot of those particles of gas. They do fusion reactions, and as we go through the semester, we'll learn how we fill in this periodic table using the fusion reactions inside of stars. Those fusion reactions will eventually stop working, and the stars will blow themselves up and recycle that material back into the galaxy. And like I said, Earth is a consequence of all of this stuff. So after the Big Bang, the only materials that were around were hydrogen and helium. So everything lower on the periodic table than those two elements were created in stars or explosions of stars. So the stuff that we're made out of, carbon, the silica that the Earth is made out of, the oxygen that makes up water and that we breathe, all of that stuff is star stuff. And the way I like to think about humanity is we are the universe's attempt at understanding itself. So how do we, as a species, compare to the kind of the history of the universe? So if we shrink the time scale of the universe, which we think is 14 billion years old, if we shrink that down to a calendar year, then the Big Bang would occur on January 1st. The first few months you would have stars and galaxies forming. The Milky Way galaxy itself wouldn't form until about May. Then within the Milky Way galaxy, our solar system wouldn't form until about September. In October, the Earth's atmosphere would have oxygen in it. Once you have oxygen, you can get more complex life forms forming, like multi-celled organisms, basically. Then in December, it's not until December 19th where you would get vertebrates, which humans are vertebrates. You get plants appearing on land, dinosaurs appearing around Christmas time, animals appearing after that, dinosaurs becoming extinct December 30th, and then humanity doesn't arrive on the scene until basically the end of the last day of the calendar. So human ancestors evolved around 5 p.m. on December 31st. Modern humans don't come around until 11:58 p.m. So basically all of human history is 2 minutes on the scale of shrinking the whole timeline of the universe down to a calendar year. So humanity has hardly, we're like a footnote to the history of the universe, basically. But we've done a lot in the limited time that we've been here. So everything besides hydrogen and helium came from stars either doing fusion reactions or exploding. So all of the heavier elements besides hydrogen and helium come from astronomy, basically. And on the grand scale of the universe, we basically haven't been around for any of the history of the universe. Any questions about any of that so far? Okay. Okay, so the next thing that we'll learn about is how the Earth, which is where we live, how the Earth moves through space, and basically how everything moves around in space. So we talked about the definition of a day, and that was the time it takes for the Earth to rotate about its axis. So even if you're sitting in your seats, sitting still, you're not really sitting still. So you're sitting on an object that's spinning actually fairly quickly. So we are not quite at this level of latitude, but we're probably moving maybe 1,200 kilometers per hour. So if you wanted to convert that into miles per hour, that would be like 300 to 400 miles per hour. So faster than you would be driving in like a race car. But we don't really feel it, and we can talk about the physics of that later. So if you're standing on the North Pole, it would look like the Earth is rotating counterclockwise if you're looking down at the North Pole. And so things move, or the Earth rotates from west to east, and it rotates once every day. When we talked about the definition for a year, that was the time it takes for the Earth to go around the Sun. And so in addition to spinning around on its axis, the Earth is also moving around the Sun at a speed of one rotation or one orbit every year. And if you, this distance, this is the astronomical unit, this is the average distance between the Sun and the Earth. If you use that radius and calculate the perimeter of this circle, you can calculate how fast the Earth is moving when it does its orbital motion. And so that speed comes out to be about 100,000 kilometers per hour. So that's a few orders of magnitude faster than the Earth spinning around on its axis. The Earth spins around on its axis, but its axis of rotation is actually tilted 23.5 degrees from the plane that it orbits the Sun. And we'll come back to that next class and talk about why that's important. Okay, so the Earth is spinning on its axis and it's orbiting the Sun. The Sun is not just stationary in the Milky Way, it orbits the Milky Way at a period of about 230 million years. So we think the Earth is 4 billion years old. So it's actually gone around the Milky Way several times since its form. The distance from the Sun's orbit to the center of the Milky Way is about 27,000 light years, to give you a sense of scale. So light from the center of the Milky Way, it would take that 27,000 years to reach the Sun. There are, of course, lots of other stars in the Milky Way galaxy, and there's stars in our local neighborhood, and the stars orbit around the center of the Milky Way galaxy in this direction, but with respect to each other, they have kind of random orbits. So when we learn about galaxies in the Milky Way galaxy, we'll come back to how these stars move with respect to each other later. But they're not all moving nice and uniformly, but they do all globally go around the Milky Way galaxy. So we are inside of the Milky Way galaxy, so any picture that you see that looks like this is not necessarily going to be of the Milky Way, but it's going to be of some other galaxy that we're looking at and using that as a reference for what the Milky Way might look like. So same with this picture, right? We can't be up here and taking a picture of the Milky Way galaxy because we are inside of the Milky Way galaxy. And we don't have the technology or the time to have sent some kind of telescope out here to take this picture. So these are all either artist representations or pictures of other galaxies that we use as a reference. So this is what we think the Milky Way galaxy looks like at dawn. So the Sun would be somewhere on the outskirts of the Milky Way. In the center of the Milky Way, there's a large bulge, and then the spiral arms of the Milky Way lie along a pretty narrow plane through the center of the Milky Way. And then galaxies move with respect to each other. So within our local group and even our supercluster, there is gravitational attraction between different galaxies. So for example, the Andromeda galaxy, which is our nearest neighbor, we will eventually merge with that galaxy in billions of years. So the galaxies that are not gravitationally bound to each other, however, will all basically spread apart from each other. So this is the expansion of the universe, and so you can think about this as, so if you were making like a raisin bread in your oven, you have your dough and you put a bunch of raisins in the dough, and as you heat up your dough and turn it into bread, it expands. And so the raisins are not moving apart from each other within the dough, but the dough itself is expanding, causing the distances between the raisins to increase. So that's how we think about the expansion of the universe, is it's not the galaxies themselves kind of running away from each other, it's the universe is expanding, and so the space between the galaxies itself is expanding. And so this will have some very important consequences later on when we talk about the fate of the universe and things like dark matter and dark energy. So Hubble, you might know that name from the telescope, but there was a person named Edwin Hubble, and he was the first person to discover that galaxies are actually moving away from us. So before this, the people thought the universe was a static place, so what we see in the universe is how it always was and how it always will be. And so this discovery that galaxies are actually moving away from us was a very big paradigm shift in how we think about astronomy. And part of his findings were that not only are the galaxies moving away from us, but as you get further away, the rate at which they're moving away from us increases. So that's called the Hubble law. And the conclusion of all of this is that we're living in an expanding universe. One of the more recent findings is not only is the universe expanding, but it's expanding at an accelerated rate. So if you think about just the Big Bang, if I have all the mass concentrated in one place, and then I kind of explode it all out, eventually all that mass will want to gravitationally attract back to itself and collapse again. So this expanding universe is totally fine with that idea, right? We're just in the phase of the universe still going outwards, but eventually it'll contract back in on itself. The recent discovery is that not only is the universe expanding, but it's actually expanding at an accelerated rate. So as time goes on, we're actually moving farther and farther away from each other, faster and faster. And so this is where we have to invoke things like dark energy. So there has to be some extra energy in the universe that we previously weren't accounting for that's causing the rate of expansion to actually increase rather than slow down and eventually collapse back in on itself. So are we ever sitting still? No. The Earth is always spinning on its axis. It's always orbiting the sun. Our sun is always orbiting the center of the Milky Way galaxy. Our galaxies are all interacting gravitationally with things in the local group. And then outside of those gravitationally attracted galaxies, all the other galaxies are moving away from us at ever increasing speeds. And another point to mention is you might think, well, if everything is moving away from us, does that make us the center of the universe? And the answer to that is no. From every galaxy's point of view, every other galaxy is moving away from it. So if you go back to the bread analogy, this raisin sees all the other raisins moving away from it. But if I look at this other raisin, it also thinks all of the other raisins are moving away from it. So we're not in a special place in the center that everything is moving away from. It's just that everything is moving away from everything else.